Today we are going to talk about, continue talking about hashing, correct? So, what was hashing? You have a large universe and you want to map that to a small set 0 through n minus 1 through a function h. We saw that if we take a deterministic function h, then we cannot hope to, I mean, we will always get stuck for some set. Okay, so I am not very clear. So h is this function, and then s is a set contained in U, and you want to map the elements of S to a. So h of S, you want to have no collisions or very few collisions, correct? So you want h of S. So U is your large space, S is some function here. You want it to map, this entire thing maps to some set here. S we want to map to distinct elements. We want the function to be 1, 1 on S, ideally, correct? Now, of course, we would require this M to be greater than size of S. But can we, and we saw that you can easily get M is equal to S squared. If you take M equal to S squared, it's easy to guarantee that with high probability, there are very few collisions. And we saw that we can even ensure that if we take M is equal to order of S, we can do this by doing a two-level hash, correct? That is taking a table with M is equal to, so we often write size of S is equal to N. So we take M is equal to order N, and then we take, we build a table in which in the ith slot, if there are Ni items, we use this scheme to build a table of size summation Ni squared. I mean, there's a small table for each Ni, for each I, which is of size Ni squared. And we saw that we can, with high probability, bound this to be order of N. So the total storage is still linear. Correct? Are you with me?
Yes, sir.
Okay. So now today we will see a particular realization of these hash functions. We'll see a couple of ways to define universal hash families. Correct? So one way to do this is to use a large prime. Correct? So this is not a very practical way, but it's easy to analyze this. So first, let us do this. So take a prime P, large prime P, greater than size of the universe. This is a massive prime, correct? We don't know how to create such primes, but nevertheless, let's assume that this prime P, we have a handle on this prime. Okay? So what do? We take the hash function is h of x, and that's parameterized by two quantities a and b. This is equal to ax plus b mod p mod n. Correct? Here a belongs to 1 through p minus 1, the non-zero quantity, a random non-zero quantity chosen from 1 through p minus 1, and B is a random quantity chosen from 0 to p minus 1. Correct? Okay. So is the definition of this hash function clear?
Sir, so the keys are integers?
The keys are, sorry?
Integers?
Keys are integers, yes.
Okay.
Keys are integers, and the size of the universe is 2 to the size of the keys, correct? So if the key size is k, then u is equal to u is something less than 2 to the k, and p is greater than u, correct?
Okay.
Sorry. U is less than 2 to the k, and yeah, correct? So last time we saw that if you take 80 bits, 80 characters, and each character is 7 bits, and this is 560 bits, so your prime P should be 560 bits long. Okay. And your M will be small depending on your S. Okay. So why is this a universal hash family? By universal hash family, we mean H is universal if the probability that Hx equal to Hy is less than equal to 1 upon M for all x comma y belonging to the universe, and H is picked randomly from the set from the thing H. Correct? So what we have to prove is that probability over A and B picked randomly from these sets so A is picked from the set 1 through p minus 1, and B is picked randomly from the set 0 till p minus 1. The probability of AX plus B mod P, correct? This is mod M is equal to AY plus B P mod M is less than equal to 1 by M. Correct? This is what we require to prove. Correct? So the crucial observation is if you ignore the mod M part, first just let us look at AX plus B equal to R mod P and AY plus B equal to S mod P for R comma S belonging to 0 through p minus 1. Correct? So fix some R and S in 0 to p minus 1. Then I claim that there is a unique solution to this for RS belonging to p minus 1, R not equal to S, and X is not equal to Y. Okay, so if I give you this 4 tuple RSXY, which are pairwise not equal, then there is a unique solution for A and B of the system of equations. Okay? Unique A comma B that solves this system. Why is that? Well, it's just a linear system of equations. You can just solve for it. Correct? So how do you solve for it? First, you subtract the two things. So A times X minus Y is equal to R minus S mod P, which means that A is equal to R minus S into X minus Y inverse mod P, where this inverse is minus Y. Okay?
Yes, sir.
equal implies that hello. So so you can for any, so basically that you have any Z is not equal to P implies Z inverse such that Z into Z inverse is constant. So that this exists. Well, Z is not divisible by P. P is not divisible by Z because P is a prime, and therefore there exists alpha and beta such that alpha Z plus beta P is equal to 1 modulo is equal to 1. I mean, the GCD of Z and P is 1, correct? Because P is a prime and Z is not divisible by P, correct? So their GCD is 1. So now you just go modulo P and you see that alpha is equal to Z inverse. So alpha Z is congruent to 1 modulo P. Correct? So this is just an aside, which implies alpha is equal to Z inverse. Correct? So now therefore we can invert x minus y is safe. X minus y are two numbers smaller than p minus 1, which are not equal. So they are inverted. And now you just substitute this in the previous equations to get your b. So what do you get? B is equal to r minus x mod p. This is equal to r minus, so you can simplify this, r minus s upon x minus y mod p, and this is just r minus x minus x. So this is just equal to sx minus ry into x minus y inverse mod p. Correct? So we have seen that, we see that there is a unique solution. So has a unique solution. Correct? Now our hash functions takes an additional mod m. Correct? So now what is so the point is that when is HAB x equal to HAB y, when the unique solution that you get for AX plus this R and S are congruent modulo P, correct? So if and only if R is congruent to S modulo P, modulo M, sorry, correct? And what is the probability of this happening? Tell me. It is equal to probability that R is congruent to S modulo M is equal to 1 upon P into P minus 1 times N, where N is the number of solutions of R equal to S modulo M. Number of solutions of R equal to S modulo M, where R is not equal to S. Okay? Are you with me?
So can you repeat the last part?
So I'm saying, when is R equal to S? R is randomly distributed from 0 to P minus 1 because A and B are.
Okay,
correct?
sir.
Now, the probability that we saw that AX, this has a unique solution, correct? So for a fixed R and S, the probability that AX plus B is equal to R and AY plus B equal to S is 1 upon P into P minus 1.
Okay.
You pick A and B randomly, and there's a unique solution. So that you get R and S. R can be fixed in, let's say, P ways, and S can be fixed in the remaining P minus 1 ways because R is not equal to S. Correct?
Yes.
So the probability that modulo P is equal to R and AY plus B modulo P is equal to S is equal to 1 upon P into P minus 1. Correct?
Yes, sir.
So now what are bad values for R and S? The ones that lie in this set. Number of solutions of R equal to S modulo M. And there are n of them, correct? Therefore, we get correct?
Yes,
so
sir.
therefore, we this probability of AX plus B, whatever, HX is equal to N up is exactly this quantity, correct? Okay. So now we want to say what is N into P minus 1. So what is N? I claim N is less than equal to P into P minus 1 by N. Why is this so? Because R can take P values, S can take P minus 1 values. Together, R and S can take P into P minus 1 values. Every mth value. So basically, we want to say what is a bad RS pair when R minus S is divisible by N. Right? So roughly, how many such RS pairs are there? R and S are both. The total number of values divided by N. M divides R minus S. Correct? No, meaning if and only if so what is the probability that for randomly chosen R and S, M divides R minus S is equal to total number of R minus S divided by M. So the bad probability is so the less than, I should say. So bad probability is less than P into P minus 1 by M divided by P into P minus. No, what am I writing? sorry, P minus no, what am I making? Sorry, the other way around. So I should say the probability of this happening is no. 1 second. No, number n is less than. I should. Sorry, I'm making hash of things. So n is less than p into p minus 1 by m. Correct. There's 1 by mth probability that an RS pair is bad. So there are total number of pairs is pp minus 1. So n is less than pp minus 1. So therefore, this bad probability is less than equal to p into p minus 1 by m by p into p minus 1 is equal to 1 by n. Correct? Correct?
Yes, sir.
Okay. So therefore we are done. Correct? We have shown that we can create a hash function using this way. Correct? But it's impractical to get such a large prime P. Correct? So let's see another scheme. There are many such schemes. I will just tell you about one more scheme, which consists of the following. So suppose you have your U is U is some power of 2 or something. U is some power of 2 to the power k, 2 to the power, let's say k times n, correct? Where your universe where your key size, where your so you are hashing from your functions h are from u to 0 through m minus 1. Correct? So suppose u is 2 to the km. Correct? So therefore you can represent a key with km bit numbers. I'm making mistakes. Give me 1 second. Not 2 to the key, 2 to the sorry, made a mistake. So let me say m to the k. Yeah. So think of m as m is a prime, a small prime, correct? And your universe is of size m to the k, correct? So you can write a key with a radix m number of length of k digits. Correct? Even this should work, I think. Yeah. Yeah. So am I making sense? Till now, is it clear what I'm saying? So you take your key, the key k is equal to some number x1, x2, x sub k, where each of these xi's are less than m. correct? Less than n, less than equal to n minus 1. So you are each one you put down in there. And now what do you so the hash function uses k random numbers from residues from 0 through m minus 1. Correct? Random residues from 0 through n minus 1. Correct? So say R1 till R sub k, and now your hash function h R1 till Rk of x is just summation xi ri xi I is equal to 1 to k modulo m. Correct? Are you with me?
Yes, sir.
Okay. So so you have taken these k random numbers and take the inner product with these xi's. You have written your key in terms of these xi's, broken up into log m, and take the inner product. And I claim that this is a universal hash function. Why is that? So we want to prove that, let me write it like this, is equal to HRY. Probability of this happening is lesser than equal to 1 by n. Want to show. Okay. So how do we do that? Well, that's not very hard. Let's do it. So firstly, for x not equal to y, correct? So if x is not equal to y, means that there exists an I through in 1 through k, such that xi is not equal to yi. Correct? All the digits of x and y cannot be the same. If they differ, there's some digit in which they differ in radix n. Correct? Because x is not equal to y, so some digit of x comma y must be different in radix m. Correct? So now let's focus on I. Correct? So while choosing these random bits R, let's suppose we have chosen the random bits for all j belonging to k minus I. Correct? So let's focus on, so whatever values they get, correct? So now what is HR of x? This is equal to Ri xi plus some stuff, correct? Plus a number, plus this Rj xj, j is not equal to I, correct? And similarly, HR of x is equal to HR of y is equal to Ry plus summation j is not equal to I, Rj xj, Rj yj, correct? So now let's call this quantity something, let's call this capital X, let's call this capital Y, correct? So if these two quantities are equal, then Ri plus xi, Ri xi plus x is equal to Ri yi plus y. Correct? Are you with me?
Yes, sir.
And now Ri into xi minus yi is equal to y minus x. Correct? And all this calculation is modulo m. Correct? When we say this is all modulo m, mod m, mod m, mod m. Correct? And m, recall, was a prime, a small prime. So and also xi, small xi is not equal to small yi by assumption. I has been picked this way. So this means that xi minus yi inverse mod m exists. Correct? Xi minus yi is invertible modulo m, which means that Ri is equal to y minus x, xi minus yi inverse modulo m. Correct? Are you with me?
Yes, sir.
So now there is a unique Ri that works, that gives a bad result. So if you have fixed this x and y earlier, this quantity earlier, after this, you should keep one. This and this by inverse just 1 by n. So this is some quantity. Ri is equal to that quantity occurs with probability 1 by n. Because Ri is chosen from 1 to
sir, your voice is breaking.
probability of 1 and 6. Now is it better? Hello? Is it better now?
Yes, sir. Yes, sir.
Okay. So this is equal to 1 by n, correct? This is exactly equal to 1 by n. So we have proved something slightly stronger, that instead of less than equal to 1 by m, we get exactly equal to 1 by m for x not equal to y. Correct? So therefore we are done with this. Correct? So now any questions?
Sir, actually, could you repeat the last part?
Sure. So from which point? This page or the previous page? Which
Sir, like how, like the final equality, like how did we get it? Like I couldn't hear the.
So you have set the capital X and capital Y by choosing the first. So X comma Y determined by picking R, except for Ri, you pick the other R1 through K, Ri through R1 through Rk, correct? So X and Y determined by this. Only Ri is missing, correct? Now, so this gives value X and Y. We don't care whether they are same, different, whatever, correct? But we know that in the ith place, xi minus yi is non-zero, modulo m, because that's how we picked I. Correct? So therefore the inverse exists, and therefore Ri must be equal to y minus x, xi minus yi inverse modulo m if there is a collision, if hrx equal to hry. Correct? So the probability of Ri equal to some value R naught or R is just 1 by n. Correct?
Yes, sir. Thank you, sir.
So this is just 1 by n. Correct? Yeah, more questions? Okay, so now having told you a little bit about hashing, let's see one more application of hashing. Correct? This is the so-called Bloom filters. Or Bloom filter. Correct? And this supports the following operations. So this is a space efficient data structure. And what are the operations supported by it? Firstly, init. Then you want to do insert an element. And then you want to query X. Is X present as X being inserted or not? These are the only 3 operations that we want to support. And so basically we want to insert and query both in small time. Correct? And we will do this. So let's see how to do this. We use the idea of hash functions to do this. So what we will do is we will take in the init, we will create an array consisting of m many bits. Correct? M bits. And now to insert X, and we will also pick k hash functions from u to n, whatever, n0, n-1. Correct? So you will create these hash functions. Correct? K hash functions, which are independent. Okay. So now the idea is how do you insert X? So H1, H2, Hk. Correct? So you to insert X, you do A of for I is equal to 1 to K, do A of, so call this A of Hi of X equal to 1. That's it. So you put a 1 in each of the K spots given by the hash values. Correct? And to query X, what do you do? For I is equal to 1 to K, do if A of Hi X equal to Hi X equal to 0, then return false. correct? And finally return true. Correct? So what is happening here? Do you see what is happening here? If all the hash functions, so you will check the hash function values correct? So if you will hash this x onto wherever, so HIX would point to a bit, and if this bit is 0, means that we have definitely not hashed anything to this, correct? Meaning, but it could happen that some bit is 1, and that's because there is a collision. That some HIX is equal to some HJY equal to correct. There exists IJ so that this happens, correct? Then we would get a false positive, correct? But we eliminate the probability of false positives by repeating multiple times, k times. So the property is, the property of this data structure is that no false negatives. That is, if the data set, if the Bloom filter says X does not belong to, says query X is, says not present, then it must be correct. But, and a small probability of false positive. That is, Bloom filter says, says present.
Sir, screen isn't visible.
Yeah, one second. Sorry, something went wrong. Can you see the screen? No. Can you see the screen now?
Yes, sir.
Okay. So small Bloom filter says present, but with small probability, this is not the case. So how do we prove this? So I will give a heuristic argument which is not entirely correct, but it can be made correct by using concentration bounds, which I will not get into. But let's try to prove it approximately, correct? So what is the probability of getting so what is the probability that so you set what is the probability of setting a bit to 1? No, so what I'm claiming is this. So the probability that a bit is set to 1 is 1 by m. Once you add a bit, if you add a single this thing, you set the bit with probability by a single hash function, the probability of a wrong bit being set to 1 is 1 by m. So the probability that none of the bits is wrong. What I'm saying. So 1 minus 1 by m is the probability that so HIX is equal to so a particular bit is set to 1 with probability 1 by n, correct? You have m bits. When you insert a bit is set to 1 with probability 1 by m. So the probability of that it is not set to 1 is 1 minus 1 by m. So in k times it is not set to 1, bit is is equal to 1 minus 1 upon k, m to the k in one insertion, correct? So this is roughly equal to 1 minus 1 by m whole to the power m into m into k by m. And this is just by the usual approximation e to the power minus 1 whole to the power k by m, correct? So so after n insertions, this is in a single insertion, correct? That a bit is not set to 1 is equal to e to the power minus k by m. After n insertions, a bit is 0 is roughly equal to e to the power minus kn by m. And now the probability that this is where the heuristic part comes in, probability that all the bits queried for HIX, I belonging to K, are 1. So AHIX equal to, by this I just mean all that A of HIX equal to 1 for all I if X does not belong to, X is not inserted. So if X is not inserted, is roughly 1 minus e to the power minus k n by m whole to the power k. Correct? Why is this? I mean, I'm just saying, I just invert the probability. This is the probability of there being a 0. 1 minus this is the probability of there being a 1. All of them are 1. Assuming they are assuming that they are distributed, that the hash functions are independent, and the bits are randomly distributed is this. And now you can, and this can be made very small by choosing even. So by choosing n and by m appropriately, this can be made very small. Correct? So you want to, do you see my point?
Yes, sir.
So if n by m is not large, it's not very small. So you are inserting not many more elements than there are slots in this thing. You can make this. So basically, if you take k n by m is equal to ln2, correct? If you adjust the so what are the parameters you have available to you? They are m and k, and you take them so that kn by m is ln2. Then you get 1 minus e to the power minus ln2 here, which is to the power k, which is equal to 1 minus half to the power k. This is 1 upon 2 to the k, correct? So what I'm saying is that by choosing m to be not very small, so what does this mean? This means that m is equal to kn by ln2. Correct? So m is not very large, and yet you can store that which things have been inserted and which things have not been inserted with high probability very efficiently. Correct? Are you with me?
Yes, sir.
So this is a simple data structure that does this, and there are many variants of this which are present. So that is all I had to say about today. If there are questions, I'll be happy to answer.
Sir, can you go to the part where you proved that HAB is a set of universal hash functions?
Wait, which one?
Yeah, in the beginning, you proved that HAB is a family of.
HAB.
Yeah. Yeah.
Huh.
Yes, sir. So can you just explain the process? I understood the calculation. Can you explain the problem, sir? Like what should we like to prove that HAB is a family of universal hash functions? Like what should we prove?
What we want to that prove this, that the probability that there is a collision is small. Two hash functions. Tell me.
So the hash functions can be different, right?
The hash functions are the same.
For the same hash functions, the probability that okay.
Meaning for the same hash, two different key values you are hashing onto the same spot is small. Meaning this hash function is given by A and B, correct?
Yes, sir.
Now you take an x, a key x, and map it onto something, correct? So it will map onto this value.
Yeah.
You take a key y and you map onto this value, that is this. These two collide only with a small probability. Correct? They are both mapped to the same value in the table, same index in the table. Occurs is a low probability event is what we want to prove. Recall that we had used this to show perfect hashing of linear size last time. And now we are instantiating it by this, correct?
Okay, sir. Yeah, got it.
Okay. Yeah, more questions?
Sir, I'm a little confused with this in general, sir. One question.
Tell me.
One question is like for what we were just talking about. The what we need to show that a family is universal. What are we fixing and what are we varying over, sir, when we're calculating this probability?
So let's see this. So we are varying. So what are we fixing and what are we varying? The family is given by two parameters A and B, which are picked uniformly at random from 1 through p minus 1 and 0 through p minus 1. Okay?
Okay, sir.
And that's it. So this family, once you fix A and B, this family becomes fixed. Once you pick A and B, this HAB gets fixed, this function. Now you can, so it maps X to AX plus B, modulo P, modulo M. So you ask what is P? So P is, so okay, that's what you meant. Okay, let me start again.
So not P, exactly, sir. My question was like, are we saying for a given function, the probability that there is a collision is low, or we're varying over all functions also, right?
We are varying over all functions. The functions are parameterized by A and B.
Okay.
So we are, so there are, how many functions are there you can count, correct?
Yeah. Okay, sir, so
they are given by the number of A's and B's.
Yes, sir.
Yeah.
So yes,
basically, guess a A and guess a B, or you tell me. So, what is the question? Tell me again.
So could I phrase what we want to prove like this?
Yeah, sure.
There are given a 4-tuple A, B, X, Y. There is a collision if this particular equation happens to hold. So we want to find the probability that this 4-tuple is bad, quote unquote, by our definition of this. Is that what we're doing?
So this 4-tuple is bad, yes, but then we will go over for all X, Y. X, Y, not U, but for all X, Y, and S. For U, we cannot say, but for all X, Y, and S, the size of S is N. We will do this.
So, but we would vary over A and B also, right?
A and B are randomly chosen. So you fix A and B by taking a random choice.
Okay.
See, think of it this way. We said that we have 560 bits are enough to represent our keys, correct?
Yes, sir.
So take a prime of 560 bits, correct? And now you pick two numbers of at most 560 bits, correct? So you take a string which is 1020 bits long, correct? Those give you your A and B. And now you do this arithmetic. Given a key, you multiply this A and B, you compute this linear function AX plus B, reduce modulo P, and then reduce this thing modulo M. M is small. M is, I don't know, a number of items, some 10,000 or something, correct?
Yes, sir.
So now the probability that two keys, large keys, collide is small. They are hashed onto the same value from 1 through 10,000 is very small. Is less than 1 upon 10,000. That's what we want to prove, correct?
Okay, I think I got what you're saying, sir. But then I have another question. It's a little vague. I don't know how to phrase it properly. But
Okay.
so sort of, if I understood this correctly, we're focusing on one function and then saying that the probability of a collision given that function is very low.
No,
But
not on one function. We are focusing on a family of functions. The family is given by these 1020 bits. So you guess a random function in this by guessing these, by choosing these 1020 bits arbitrarily.
okay, sir.
And then you are
So
saying, yeah, tell me.
then our probability is also varying over A and B, right?
Yes, the probabilities over A and B.
Okay, yeah, that's okay. That's what I was confused about.
Okay.
Yeah.
So
Okay.
A and B are the only thing which are chosen randomly. Everything else is deterministic. Correct?
Okay, I think I see it now, sir.
Okay.
Okay, thank you, sir.
Okay, you're welcome. So more questions? Okay, if there are no more questions, then I'll conclude for the day, and we meet next Tuesday. We will have a quiz next Thursday. I am a bit busy till Tuesday, so that's why I don't have the time to schedule it on Tuesday. That's why I'll keep it on Thursday. And yeah. So there are 3 more classes remaining, correct? Hello?
Sir, we don't know, sir.
Why not?
So the classes are till April end?
No, the first week of May. And
Okay.
3rd is a holiday, correct? I believe Tuesday, the Tuesday after next is a holiday. Anyway, I'll also check, you also check, correct? Okay.
Okay, sir.
Okay, thanks. Bye.
Thank you,
Thank you,
sir.
sir.
Thanks. Bye.